Are there any questions on the homework?
3.2, 16, 417, and the same.
So 3.2, number 17. This is asking us to come up with an equation of a normal line, and it says a normal line is perpendicular to another line or a tangent line. So the process here is to find the equation of the tangent line, and then to find the normal line, we have to describe the line that is perpendicular to our tangent line. So maybe the major component that was long forgotten, how do we describe a perpendicular line when we compare it to another line?
Reciprocal.
Yeah, so that's close. Slopes are not only the reciprocal, but the
Negative?
yeah, the negative reciprocal. So negative reciprocals of one another. That is, two lines are perpendicular if the slope of line 1 is the negative -1 over the slope. Do you remember that vaguely? You're long forgotten. For example, y equals to 2x minus 3. And we'll say this is y1, and y2 is negative 1/2 x plus 12, I guess. Those two lines are perpendicular. So other than that, I think everything we've been doing has sort of lent itself to this problem. So we come up with the equation of the tangent line, which means we find the slope of the tangent line at this point, construct the tangent line at that point, and then use the negative reciprocal as the slope to find the equation of the new line. Perpendicular to the line, tangent. Okay. Does that make sense? Okay, so this is in 3.2. So technically we don't have our shortcut methods to take the derivative of that in 3.2. Oops. So we need to first find the slope of the tangent line at the point. We're given a point. What you really could, since it's sort of an intermediate process here, you could find the derivative function and then plug in the x value to determine the slope, or we could use one of the two formulas that we had for determining the slope of the tangent line at a given point. Those two formulas involved a And there were a plus h minus f of a. Y'all remember those? So I don't think it really matters what approach we take to find the derivative, which one of the three formulas we use. But finding the derivative function using the definition, there will be one question like that on the exam. So let's just go ahead and find the derivative function using the definition, and then we'll plug our x value in. So that's the definition of the derivative, and our function was x squared minus 3x. So when we're using that definition, really the only thing you need to compute is f of x plus h, and then we plug everything into that derivative. So let's compute f evaluated at x plus h. We have x plus h squared minus 3 times x plus h. Expand these. We have x squared plus 2 xh plus h squared minus 3x minus 3h. So that's what f of x plus h is. And once we plug that into the definition and subtract off f of x, some of the terms will cancel. All right, so we have f prime is this limit of our f of x plus h. Minus f of x. So just be mindful you're subtracting off the entire function. So we'll just minus the quantity x squared minus 3x. And then all of this is over h. And so that means the x squared term cancels with this negative x squared, and the negative 3x cancels with this positive 3x. And notice what we have left over, 2xh, h squared, and minus 3h. All three terms that are left over have an h in common, so we'll factor that h out. Numerator. Again, if you want to simplify the difference quotient first and then compute the limit as h goes to 0 on the simplified version, feel free to do that, but just be careful of your notation. Don't simplify the difference quotient and then say that this stuff is equal to the function, right? Make sure you have the limit as a last step if you're doing so. Do y'all have any questions on that? All right, so that's just the limit as h goes to 0 on 2x plus h minus 3. So we get 2x minus 3 as the derivative. Kind of keeping in the back of our mind that we know some shortcuts to take a derivative. When we look at the function x squared minus 3x, we can use the power rule. So the derivative of x squared is 2x. The derivative of negative 3x is negative 3. So we can kind of use those shortcuts to check our work. when we're asked to use the definition of the derivative. So 2x minus 3. And remember, what that gives us is the slope of the tangent line at any x, or at any point on the original function x squared minus 3x. So that's part of our computation, but we were asked to find the slope of the tangent line at the point 510. So the slope of the tangent line at 510 would be f prime evaluated at 5. Which gives us 7.
So since it's perpendicular, is it just going to turn into -1/7? Is this slope?
Right, yeah, and so the line we want is perpendicular to this line, so the slope of the perpendicular line will have a slope of -1/7. Yeah, so let's look at the instructions again. Find the equation of the line. Okay, yeah.
So now instead of, so y1, y minus y1 equals then tangent of x minus x1.
Yeah.
Would we plug in the 5 and the 10 and then just change it to -1/7?
Yeah, right. So we're just gonna,
The intercept would remain the same?
well, so we're given the tangent line at this point. We can now construct that. And then the instructions believe they just want us to find a perpendicular line that is tangent to the tangent line, rather. So it doesn't specify, find a perpendicular line. Like if I draw some line, particularly, my tangent line passing through this point, unless I read it incorrectly, it doesn't specify, do we want this perpendicular line here? Do we want this perpendicular line? There's infinitely many perpendicular lines we can construct to the tangent line. So I would assume that they would want us just to construct the normal line at the given point, 510. So I would just use the point 510. So then, the second step, equation of the tangent line. So we have y minus y1 equals the slope of our tangent line times x minus x1. It's worth pointing out again that as we move forward with our derivative rules, when we're asked to find the equation of the tangent line, this slope of your tangent line that you plug into point slope formula, you're always going to plug in a number. You're never going to plug in a function. I see people wanting to plug in the derivative function here. That's not correct. The slope of any line is always a number. It's never a function. So what do we get? We get y equals to 7x. We've got a minus 35 plus 10. So there's the equation of the tangent line. So the normal line slope, as we mentioned, since it's perpendicular, the normal line slope is -1/7. And then we'll just construct the equation of that particular line at the point 510. Is that all right? Do you have any questions over that?
So whatever you're computing with the -1/7 is at 510 is your answer?
Yeah, right. So whatever line we get here as that result, this is our answer.
So do we actually have to compute the equation of the tangent line?
Yeah, I mean, I guess it's sort of redundant to compute the actual equation of the tangent line. Really, to describe a perpendicular line, we just needed a point and the fact that its slope was the negative reciprocal of 7. So we didn't necessarily need the equation of the tangent line.
Thank you.
You're welcome. Does anyone have any other questions? So we left off in 3.3. These last few examples we looked at, or the last example we looked at, example 3, we had to simplify the function first before we took the derivative. So we distributed square root of x into x minus 1, and that gave us x to the 3/2 minus x to the 1/2. So that's equivalent to our function. Then we applied the power rule to both terms of x to find the derivative. Once we learned the product rule, we could compute that derivative using the product rule. But honestly, even with the product rule, the way we went about it here, where we simplified the function first and then found the derivative, that's going to be much more efficient. So it's important when you're asked to take a derivative, if you can simplify the function, simplify it first and then take the derivative. Okay, same thing with example 4. Once we learn a quotient rule, we can take the derivative of that, but it's going to be a lot more efficient just to simplify the function first. So we're going to simplify f of x as x squared minus 1, and then we're going to take the derivative of that. So remember the alternative notation of f prime, or the derivative, we could write that as d over dx, which means take the derivative of this function. So the derivative of x squared minus 1 would give us what?
2x.
2x. Do y'all agree? Derivative of x squared, power rule, 2x, minus the derivative of a constant, which is 0. Similar situation for function 5. Before we look at the simplified version of f, we see that f is not defined when x is equal to 1. So if we looked at the graph of f of x, we've got a hole there at x equal to 1. We wouldn't expect us to be able to find a derivative on the function where it's undefined, right? It doesn't make sense. Like if my function looks like this, and it says find the derivative at this point, the function doesn't exist there, so you can't have a tangent line there. So we simplify f of x, difference of squares up top cancels out with the factor of x minus 1 on the bottom. So f of x is a pretty simple function. It's just x plus 1, but we do have a hole at x equal to 1. Or removable discontinuity. So the original function is the same as x plus 1 with a hole at 1, 2. And then finding that derivative. What's the derivative of x plus 1? Equal to 1. Now the derivative, the slope of the tangent line on any linear function that's not horizontal is always just the slope of the line itself. So here's, oops. So the original function f of x looks like this. Sorry, my line is terrible. So the derivative exists as long as we're not asked to find the derivative at the point 1, 2, because there is no point at 1, 2. Do y'all have any questions on that? I'm not sure, for those of you that printed out 3.3, was this page there? All right, I'm not sure what happened to this section as far as the notes go. But it is mentioned in 3.3, higher order derivatives, second derivative, third derivative, etc. So what they're defining here is f double prime, which is the second derivative. And they've said that here the second derivative is the derivative of the first derivative. So the third derivative is the derivative of the second derivative. The fifth derivative is the derivative of the fourth derivative, so forth. So the nth derivative is the derivative of the n minus 1th derivative, the previous derivative.
What would that be used for?
So the physical context of second derivative is typically, for us, it's in context of if you're given a position function, the rate of change of position with respect to time gives you a velocity. The rate of change of velocity with respect to time gives you acceleration. The rate of change of velocity, the derivative of acceleration gives you what in physics is called jerk. And then the derivative of jerk is snap. And then derivative of snap is crackle, derivative of crackle is pop. So what is that, 5 derivatives? So really, I mean, in a physics setting, it might not be uncommon to look at, a 5th derivative for something. Primarily, for us in this class, it's only up to a second derivative that we're concerned with, because second derivative of position gives us acceleration, as we'll see later, and second derivative is also used in chapter 4 to determine a specific thing about a given function. So let's look at an example. So example, let's find the third derivative. Which would be f triple prime of x. Sometimes after like the second prime, especially for like 4th, 5th, 6th derivatives, sometimes instead of writing or using the tick marks or the primes, we would write it as just the number up here in parentheses. So that's notation for the third derivative. So find the third derivative of f of x equals to, let's do the square root of x. So the first derivative of the square root of x is what?
1/2 x to the
Negative 1/2, right? So we want to view this. Remember radicals, when we see them, we want to think about them in terms of powers, so we can utilize the power rule. So that we bring the power out front to multiply x to the 1 less power. So first derivative, 1/2 x to the negative 1/2. And the second derivative just means to take the derivative of the first derivative. You don't have to write all of this notation out, but I'm going to do this. So what's the derivative of the first derivative?
Negative 1/4 x to the negative 3/2.
Right, good. So power comes out to multiply, negative 1/2 times the 1/2 gives us negative 1/4. And then we subtract 1 from the power. Negative 1/2 minus 1 is negative 3/2. And then the third derivative, f triple prime of x is the derivative of the second derivative. So the derivative of this function. That'll give us the third derivative. So we have negative 3/2 times negative 1/4. So we have 3/8 x to the negative 5/2. Like I said, typically we do not go past the second derivative for the things we do in this course, but it is possible to keep taking derivatives. Some functions have, like polynomials, eventually you'll get to where their derivative is 0. And so the next derivative, the derivative of 0 is 0, the next derivative is 0, the next derivative is 0, right? So at some point, sometimes functions, their derivatives vanish because we end up with 0. Other times, function like this, for instance, we would continually be able to take derivatives. So we could find the 30,000th derivative of this. I don't know why we would, but we can. Do y'all have any questions on that example or higher order derivatives in general? We're behind, so I'm going to skip these two examples. Just finding the equation of the tangent line at the given point. If you do want to work these as additional practice, I'll write the answers down. But I'm not going to work these. So number 1, you should get y plus 1 equals negative 6 times x minus 1. And for function 2, y minus 1/4 equals to negative 3/4 times x minus 0. Any other questions on 3.3 before we move on? So 3.4, we're going to look at the product and the quotient rule. So this is really where the derivative rules start to pick up. Like I said, I would use like note cards or just practice writing these rules down over and over, whatever it takes for you to get to remember these rules. Because in the next section, for instance, when we learn derivative of the trig functions, like the textbook will justify the derivative of sine and cosine using the definition, and then they just present you with all 6 derivatives for trig functions. And then so they look at it, one example maybe, and then they go right into, okay, well here's a function that's e to the x times sine x divided by x to the 4th plus x squared, right? So then all of these rules start intermingling with each other, and it can really snowball if you're not keeping up with them. So if you can, keep up with them. All right, I think the product rule is down below. But the idea of the product rule, just to kind of motivate this and show us what we can't do as far as what the product rule is not. Let's consider 2 functions. F is x to the 5th, and g of x is x squared. And if we wanted to compute or to find the derivative of f of x times g of x, we can say, well, that's equivalent to the derivative of x to the 5th times x squared. This is a simple example to kind of show us, again, what we can't do. Well, we know that's equivalent to, we're simplifying the function, that's equivalent to finding the derivative of x to the 7th, which we know indefinitely from the previous section is 7x to the 6th. Right?
But we're taking the derivative of each one. Oh, so we're seeing this as a one, not two.
Yeah. So, although we don't know the product rule just yet, can we all agree that this is an appropriate way to handle the product? The derivative of that product? We just simplify the product first. But oftentimes you can't simplify a product like e to the x times sine x. You can't simplify that. So the question is that the same thing if I take the derivative of this product? Can I just take the product of the derivatives? In other words, can I just distribute the derivative operator across a product? And I say that's the derivative of x to the 5th times the derivative of x squared. Well, the derivative of x to the 5th is 5x to the 4th. Derivative of x squared is 2x. So we get 10x to the 5th. So this was questionable because, again, we don't know the product rule just yet. We do know that this first method of computation was accurate, but we see that the second method of computation didn't give us the same result. So this isn't the same as this. And so what that tells us is, in order to take a derivative of a product, we can't just take the product of the derivatives. So 2 shows that the derivative of a product is not the product of the derivatives. So if only it were that simple, unfortunately it's not. So there's the actual product rule.
the proofs of the theorems in the textbook?
The proofs are in the textbook, yeah. So it says, in order to take the derivative of a product, typically the way it's remembered is we've got two things multiplying together. So often this function here we consider or label as the first function and g of x as the second. So notice the derivative is f prime times g plus f times g prime. So the way that's usually remembered is it's the first function multiplied by the derivative of the second function plus the second function times the derivative of the first. Since multiplication and addition doesn't matter what order we have there, you could also view that as the second times the derivative of the first plus the first times the derivative of the second. But typically that's how the product rule is remembered. Now I'll write that down too. What's important is the order on which these two factors are together, plus the first times the derivative of the second. So however you want to remember product rule, but that's typically how it's remembered.
Have to use it in that order? Because wouldn't it not make a difference if you just flip them?
Yeah, so that's what we did here. This is this term plus this term. The second way to look at it is this term plus this term. What's important is the first is attached to the derivative of the second, and that the second is attached to the derivative of the first.
If you had like three functions.
That's a good question. What if you had three functions? What if it was f times g times h?
Would it have like 4 parts to it?
So it gets a little more complex. We can certainly discuss that. Okay, so derivative of a product first times the derivative of the second plus the second times the derivative of the first. Now when we look at other derivative rules, the one thing to point out is with the quotient rule and the product rule, their additional derivatives are showing up, right? So if we say the derivative of this product is this first term times the derivative of the second times the derivative of the first, you're not done finding the derivative because we can't define a derivative in terms of a derivative, right? That's like saying solve for y and you say that y is 2y plus x. You haven't solved for y. Here we haven't technically fully found the derivative. So we'll see a couple of rules that do display a derivative in terms of other derivatives. And it's really important that at face value we take this formula as it is. I recommend writing it out, whatever the first function is, the derivative of the second function, explicitly writing that out. So you know once I've utilized this thing right here, I have taken the derivative of that particular product, but any additional derivatives that show up, I need to, maybe off to the side, compute them separately and insert those back into the formula. Okay, so leaving derivative of the second here and derivative of the first isn't anything that we do. Derivatives aren't defined in terms of other derivatives. So yeah, the question was, what if we had to take the derivative of three functions, product of three functions? So f times g times h. In our definition above here does really cover three functions. It covers 100 functions. It's just the product rule, we look at two functions at a time. So however we wanted to arrange that, we could say that f of x is the first and g times h is the second. So then you've got two product rules ultimately that you have to apply.
So you'd simplify it, like multiplying them beforehand?
If you could multiply g and h together to simplify, like if it were x squared times x to the fifth, yeah, that would make life much easier. But what if this were like a log times an exponential times a trig, where you couldn't simplify them? So the derivative rules, although they're simpler because we don't have to compute the limit as h approaches 0, blah, 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 they can get very complex depending on the function. So the way we would have to approach this is we would have to say, well, this is equal to the first times the derivative of the second So see, I'm not worried about how many functions I have. All I'm worried about is, well, it's a product. So I'm just going to apply the product rule. So it's the first times the derivative of the second. Let's see if I can fit this in here. Plus the second times the derivative of the first. Yeah, so that's the product rule applied. So that's what I need to do, right? It's a product, there's my product rule. Then I look, as a result of my product rule, what other derivatives do I have to find? So then off to the side, we would say here, aside, I have to compute the derivative of g times h and I have to compute the derivative of f, the first factor. Once I have those two derivatives without derivatives in them, then I go back up here and I just plug those in, and that's my derivative. But we see there, to compute the derivative of g times h, as sort of a secondary step to computing the derivative, we've got to use another product rule there. So this is first times the derivative of the second plus the second times the derivative of the first. And then off to the side, we would have to compute h prime and g prime. So they can get really, really involved really quickly. Perhaps we can build up to a function like that, but we're going to look at simpler ones to begin with. Yeah.
Okay. So like what if you couldn't multiply g and h of x, so could you combine like f of x times h of x?
Yeah,
And
right.
make that the second? Does it matter which ones you combine?
Yeah, it does not matter. So like, you know, if we're asked to find this derivative, f times g times h, you know, we called f the first and g times h the second. We could call f times h the first, and we could then call g the second. Doesn't matter how we label those. The point is, with the product rule, we look at two functions of x at a time. If the other function of x is another product, then so be it. So that it doesn't matter how we group two of those together. Or if we had the derivative of 4 functions, it doesn't matter how you group the pairs. You can call whichever pair you want the first and whichever pair you want the second. Just initially, however you label them, you've got to stick with that as you take continual derivatives. Because if you mix them up, then your formula is going to be all wrong. So the proof is in the textbook. So we're proving the derivative of f of x times g of x is equal to f times g prime plus g times f prime. Just to give you a glimpse of all of the proofs of all derivative rules that we look at, we do have to fall back on the definition. So we're trying to prove the derivative of that function. So we have to say, well, it's that function evaluated at x plus h minus the function itself all over h. So that's what you have to work with. If you want to prove that that product rule is true, we have to compute the limit as h goes to 0 on this. And it's not a trivial thing. Somehow we've got to get a factor of h up top that cancels with this factor. Yeah?
For the proof, could you also write that like f prime of x times g of x plus f of x times g prime of x?
Yes.
Okay.
Yes. Okay, so yeah, if you're interested, I think a lot of these derivative proofs, for formulas anyways, are in the textbook if you're interested. This one here involves adding in 0, so we have to add in f of x times g of x plus h, and we also have to subtract that quantity in. Sorry, I ran out of room. G times x plus h. So if we add and subtract that quantity in, group terms together, factor out, the product the product rule does emerge. But we're not proving that. Just FYI. Okay. So examples. Find the derivative. Alternative notation, find f prime. It could say find dy over dx. And dy over dx is a fairly common notation that it's a little bit more descriptive of what a derivative is. If we think about what a derivative is, it's just the slope of a line at a single point. So it's a really tiny change in the y values divided by a tiny change in the x values. That's kind of what we see with the notation dy over dx. So here's f, it's x times e to the x. We can't simplify this, so we have to, a lot of these derivatives honestly are first and foremost recognizing what your function consists of. Because sometimes you see functions that have products and quotients, for example. So we have to look at like the overall structure of the function. This is a product, so we have to use the product rule. It doesn't matter what you label as the first and second, you just have to be consistent with those. So once you identified, maybe in your head, on paper, whatever, which is the first and which is the second, you just have to stick with it. So f prime, the derivative of that product, we take the first times the derivative of the second. Now I know maybe you already know what the derivative of the second term in your head is, I would not recommend just writing that down. If I say derivative, then somehow explicitly write derivative. It's gonna make a whole lot of difference, especially when we look at the chain rule in 3.7. So we're just gonna recite the rule: the first times the derivative of the second plus the second times the derivative of the first. So unless you've had a class recently in high school, or maybe last semester, and you're just really good at taking derivatives, I wouldn't try to do any of these derivatives in my head. All right, is everyone okay with that? That's just we've just explicitly stated the product rule with these two functions: first derivative of the second plus the second derivative of the first, yeah? But we wouldn't want to say that's our derivative, right? Because we have other derivatives involved. So then off to the side, maybe somewhere down below, we would want to compute what is the derivative of e to the x, and then what's the derivative of x. And once we have those additional derivatives, we'll just plug them back in for these things. So the derivative of e to the x is what? E to the x. And the derivative of x is 1. So I know maybe here it doesn't seem like it's worthwhile to write those derivatives down like we did, but trust me, as the functions get more complicated, it's going to save you a lot of hassle. So here's f prime then. We're just going to fill in the gaps. X times the derivative of e to the x, which we said was e to the x, plus e to the x times 1. So we have our derivative x e to the x plus e to the x. Do y'all have any questions on this? Now, to sort of, not to freak you out or anything, but to add to where we're going with this, in chapter 4, what we have to do is it says, here's this function, here's x e to the x, graph that function, and we have to determine where that function is increasing and decreasing, where it's concave up and where it's concave down, which involves us utilizing the first and second derivative, determining where the first and second derivative are 0. So, you know, here's our derivative. What if we wanted to know where our derivative is 0? Where does our first derivative equal to 0? When we set our first derivative equal to 0 and solve for x, what does that tell us? What does the derivative describe? Slope of the tangent line. So we're saying, here's my slope of the tangent line. When is the slope of the tangent line 0? When I solve for x, what does that tell me? A horizontal, close. Horizontal tangent line, right? So where is our tangent line horizontal? When the derivative is 0. So we do have to end up solving equations like that. Why do we care about where our tangent line's horizontal? You know, what if we had a function that was doing something like this?
Shows change of direction.
Yeah, it shows change of direction, and anytime we change direction, what happens? Specifically, when it goes from increasing to decreasing or decreasing to increasing, we're able to identify the high points and the low points because we know at this x value, my tangent line is horizontal, and at this x value, my tangent line is horizontal. So I know this may seem like an off-topic thing that we're talking about, but it really isn't. Because once you know how to find the derivative, Then you can find where the derivative is horizontal, which means for any given function, you can determine where it has a minimum and a maximum, or both, or multiple maximums or multiple minimums. And that's definitely something we look at. Because you remember graphing these types of functions in like algebra or pre-calc, there was never a valid way to determine, you know, how high this function went up before it turned back around, right? So like, you know, this would be like a pre-calculus graph. And then there's no way to know what this value is and what this value is, right? The best we could do is say, well, just pick some points in between and see where they're at, right? So with the idea of a derivative and where the derivative is horizontal, or is equal to 0 rather, then we're specifically able to find those maximums and those minimums. So it really opens up the door also, practical applications. Where is this function? How do we maximize this function and how do we minimize this function? So all of that stuff does end up showing up. So I'm really not trying to overwhelm you. I'm just trying to give you a bigger picture. So don't just get in the habit of taking a derivative and stopping, because typically it's just part of the computation. Like once we know the rate of change, then we've got to do stuff with it. Okay. So why don't you all try example 2, finding the derivative.
So not like 1
Well, you can't because they're not quite like terms because this one involves x to the negative 1 half. This one involves x to the yeah, and well, you do have a 4 times
or
that.
sine.
So you could get this.
Hey, can we get them out? No.
Like, wait, you should write that, and then go back up.
That's 4.
Yeah, but this isn't a function of x. So it's not like this.
It's half.
To the derivative of this plus the derivative of 4. It's just 4 times this function. So this is 4 times. Roots are constant.
Okay, so x is involved. It's fine. That makes sense. This is what I have, actually.
No, really just easy because then you just can look at it and just fix. Just like when I write in pencil, when I do it all looks the same.
Or you can do x.
I was actually really like those pens, and I was like, I don't know what else. She's got these
So you just, all you did here, you can take the derivative and just rewrote the square root of x as x to the left. So you still have to take the derivative of that. Right, yeah, so if you call this the first, if this is 4 times e to the x, 4 times this function of x, so this isn't considered a function of x. So after you take the derivative of this, you could just take the 4 out and multiply it after you take the derivative. So really all we have to do is take derivatives of these two things and then multiply them all by 4 and we're done. Yeah, so here you could take the 1/2 times 4. That's what the owner is simplifying. You can do 1/2 times 4. Yeah, so because when you multiply this times this times this times this, it doesn't matter like what order you combine those in. So we just say half times 4 is 2. So you could say it's x to the negative 1/2 times 2 times dx. You could say it's 2e to the x times x to the negative 1/2.
Never put them together.
You could say it's 2 times x to the negative 1/2 times e to the x.
Either of those are valid.
Definitely doesn't make this life. No.
Okay, yeah. Oh, you did it right over here. Yeah.
Okay.
So what's the other thing on the
I do right.
I just left it with negative.
Oh, it was the other thing.
So this is it?
Yeah.
So what's the thing?
I don't know.
Oh, okay.
Let me see.
Next thing.
It was just a discussion about.
Just put them together. So like,
Yeah.
create the X.
Because we're looking at that. That doesn't look
Yeah. Because it's just like when you have a bunch of things multiplied, sometimes people get confused on the order, and I think that was just the order difference.
Okay, so it's supposed to look all jumbled up. I don't like it.
Yeah.
I mean, we're doing the same thing.
Yeah, you can write it with radicals as long.
No way. No way, Jose. I'm cool.
cool being a square.
I had just done something with my bank account as well. I was like sketched out. It's the perfect timing when you give me a heart attack.
Please no one had like overthink.
He was like, yeah. So it was like an automated message. It was like, it's been canceled. All the benefits just on which is going. I was like, oh shit, this happened.
Like you're bored and you don't get another one.
Yeah.
So I tried to think of it. They're like, this stuff is so long. So I saw it.
It sucks. So it's like my journey stuff. This is the thing. Like, you should just cancel it. Maybe change one number. So I never carried on social systems in college. So it's like so like having
Yeah. Everyone has to say, people have saved, like, what the
They have all their stuff in there too.
Yeah, no,
I don't know what's up to it. So my birth certificate got removed damage, so it was like some tie-dye because it's fully deformed. So all the left when I was younger, and then for some reason it opened. I like it though.
Yeah, what?
So I wasn't sure like questions and then we went over it like solid yeah, because you don't have any more time. 11, so Tuesday's 11. That's why I was
oh, dude, don't even get me started. Oh, and then the same about you like one wrong, that shit just goes all the way back. Oh my god, and then dude, last night I forgot to like get it again. And it was like wrong, and it was like
But if you had to take organic,
oh, I forgot. In the past, like, I think you so maybe you'll see it in terms of like,
yeah, I've got to do
which I heard bad things about that. There's no point. No.
Yeah.
About 40 grand an hour.
Thank you.
That's belief.
Yeah, thank you.
So you can't have first automated, so for
I would just like to start listing things myself.
I hate when they do that. I hate when they're like, oh, there you go. Yeah, no, I sat there.
Yeah.
I don't do
What's your school mascot? I literally all know is not the mascot in graduation. That would be fun. Do you really get paid for it?
So that would just is for
That's small. That's the mascot. 1 hour is like death. Or it's so
That equals x to what's wrong? So you take the derivative of that, so derivative this goes to that, and then 1 half minus 1, or 1 half minus 1.
All right, a couple of things to point out here. As a reminder, the product rule, as it was stated to us, was like this, right? So it's one function of x times another function of x. When we see this 4 times e to the x times root x, well, 4 isn't a function of x. It's still multiplying, but it isn't a function of x. So nowhere in your computation should you have the derivative of 4 equals to 0. Okay, we have to remember that, functions of x, and we have to remember when I take the derivative of a constant times a function of x, that the constant we can pull the constant out of the derivative, right? So we take the derivative of just the function of x and then multiply the constant in, right? So just be mindful of that. Some of these things are very subtle. If you wanted to call your first factor 4e to the x, that's fine. But when you take the derivative of 4e to the x, you have to remember that 4 is a constant that gets taken out. So there's a couple of ways to look at it. I'm trying to just erase. Yeah, there we go. Okay. So one way to look at it is we can say that the derivative is equal to 4 times the derivative of e to the x times the square root of x, which is just x to the 1/2. Or we could consider this this whole thing the first. So either or, if you take the 4 out in the beginning, you've got to remember the 4 gets distributed back into both terms of the product rule. So let's just call it 4e to the x the first, and x to the 1/2 the second. So the f prime, again, I would recommend writing this out as I'm writing it out. I saw, a lot of you did have the correct answer, but you have the derivatives like separate, and you didn't have the product rule written out, like explicitly how the product rule is stated. So this is how I recommend you writing this out. We have the first times the derivative of the second plus the second times the derivative of the first. Again, as we progress the more complex functions, if you're not, or if you're writing all your derivatives out on the side before you explicitly state the rule, it's going to be really hard for you to determine when you stop taking derivatives. Okay. So then that's the product rule. We've taken the derivative, then we can address the individual derivatives that show up. So the derivative, do that here, the derivative of x to the 1/2 is 1/2 x to the negative 1/2, and the derivative of derivative of 4e to the x. At this point, we have to remember our constant multiple rule. That's 4 times the derivative of e to the x, which is just 4 times e to the x. Is everybody okay with that? Most of you had the correct answer, but I really highly recommend writing it out the way I've written it out. As you progress and do more of these and through more sections, you'll learn to understand what works for you. But at least initially, just try starting out like this. So it's sort of run out of room here. Let me move this. Oops. Okay. So then that tells us our derivative is 4e to the x times the derivative of x to the 1/2, which was 1/2 x to the negative 1/2. So that term's good. I have no more derivatives I need to take. I'm done with that. Same thing with this one, plus x to the 1/2 times 4e to the x. No more derivatives to take. I'm done. That's it. That's my derivative. Now, often we do have to end up simplifying our derivative, but for the time being, this is fine. We want to look at taking the derivative, and all of this gibberish down here below that line was kind of just showing you that the order of multiplication doesn't matter. So what we have is we have a 4 times e to the x times a 1/2 times x to the negative 1/2. And the only other thing we could do is multiply the 4 by the 1/2 to give us 2. We can't combine these terms. They're not like terms. They're different exponents. So that would be our derivative. We could perhaps talk about simplifying that if we had to determine where that function is 0. But right now, I think just getting used to the fact of taking a derivative with the product rule is primarily what we want to focus on. Yeah.
Can you only pull those out because of the constant rule?
Right.
Is that okay?
The 4?
Yeah. Okay. Well, the 4 and the 1/2. Those are both constant rules, right? At the very end there, when you try to simplify the half.
When we multiply this together. Well, so notice at this step right here, we don't have any more derivative rules to consider.
Oh, okay.
Right? Because all of our derivatives have been taken.
Okay.
So that derivative turned into that derivative turned into that. From here, no more derivatives to take. It's all a matter of algebra from there.
Okay.
So yeah, I think that's what I was getting at here. If I multiply 1, 2, 3, if if I multiply these four things together, it doesn't matter how I order them in terms of multiplication. So like I could just say, because this is like, if I say A times B times C times D, it doesn't matter how I permute all of that stuff, right? Like I could say that this is the same thing as B times D times A times C, still the same thing. But as far as the terms go, we have two terms, and they're unlike terms. So once we multiply the 4 and the half in this term, that's about as far as we can go with combining things.
Since you combine the 4 and the 1/2 there to get the 2e to the x to the negative 1/2, could you do the same there and do like 4e to the x to the positive 1/2?
Yeah, just so things kind of match up. Yeah, we could write the 4e to the x first. This could be 4e to the x times x to the 1/2. So again, this is like a times b. I could also write this like b times a if I wanted to. It doesn't change it. Is that what you were asking, Linda?
I think so.
Yeah. You just meant writing the 4e to the x first.
Because you combine the two constants there.
Yeah.
So kind of combining the two constants on the other side.
Over here, well, here we just have the constant of 4. Here we had a constant of 4 times 1/2, which is why we were able to combine those. Yeah. Any other questions on this?
So would that answer like give us full credit on an exam?
Yeah. Yeah. And honestly, I would either leave them as fractional exponents or as radicals. I wouldn't mix radicals with fractional exponents. Typically, we want to leave the fractional exponents in if we have to solve where that's equal to 0, so we know it's easier to see anyways what we should factor out. Any other questions on this? Okay, we'll take a break and then look at the quotient rule. So the quotient rule, we've got a similar thing with the product rule. We couldn't just like distribute the derivative across a product. We can't distribute the derivative across quotient. So the quotient f divided by g, the derivative is g times f prime minus f times g prime all over g squared. And there's two ways to remember this, depending on how you label f and g. Some people will call f the top function and g the bottom function, or we can call f high and g low. So there's two ways to remember, two mnemonics, I guess, to remember this. So we'll write both. If you have a preference, you can use one. So the derivative of the top over the bottom. So the quotient rule says it's the bottom. I'll just abbreviate this. Bottom times the derivative of the top minus the top times the derivative of the bottom. All over the bottom squared. Or if we think about as high over low. Low times the derivative of high minus high times the derivative of low all over the low squared. So unfortunately with the product and then quotient rules, That's as nice as we can get them. The function, depending on what it is, the derivative like that may simplify. It just really depends. So sometimes the high and low, it's read low D high minus high D low over low squared. So whatever. Again, there's derivatives appearing when we take a derivative. Explicitly write those out and off to the side compute the derivative of the top and the derivative of the bottom. Then insert them back into the formula. That way you know when you're done taking derivatives. Are there any questions initially on this quotient rule? Okay, for example, find the derivative of x plus 1 over x plus 2. So we see that function is a quotient. Quotient rule says we to take the derivative, it's the bottom function times the derivative of the top minus the top times the derivative of the bottom. And then we have to divide all of that by the bottom squared. Everyone okay with that? Any questions or issues we've done there? Even if you know the derivative automatically, even if you know the derivative of x plus 1 and the derivative of x plus 2, at least now I wouldn't recommend inserting those in there, just so we can kind of keep our bearings. Off to the side, we compute those separately. So probably not 100% necessary here to do so, but we just want to keep a consistent process. That way like I said, when we look at more complicated functions, this will help a lot. So the derivative of x plus 1 is 1, and the derivative of x plus 2 is 1. So then we want to put those back into our derivative. We've already determined the derivative formula for the quotient. So I'm going to put this stuff in appropriately. So we have f prime is x plus 2 times 1 minus the quantity x plus 1 times 1 all over x plus 2 squared. Again, that's the bottom times the derivative of the top minus the top times the derivative of the bottom. We see that in this instance, that will actually simplify. So we've got our x plus 2 minus x. The x's are gone. We've got a 2 minus 1, which is 1. So simplifies to 1, and that's our derivative.
Would you want us to expand something like that, or could we just leave it like that on the tip?
Leave it like that. No, typically when you're utilizing the quotient rule, the denominator is left squared. Don't multiply that out. Because often what happens is we end up with another factor of that up top that we can cancel. So don't expand the bottom squared. Are there any questions on this? Yeah.
When you take the derivative of x plus 1, what rule are you using to get just 1?
So the rule we're using there is we're taking, remember the derivative will distribute across sums and differences. So that's the derivative of x plus the derivative of 1, which is 1 plus 0.
Okay, thank you.
Yeah, so it's, it's subtle, the difference between like the last example where we had the 4e to the x, right, with something like this. Another thing to point out is that our function x plus 1 divided by x plus 2, it can also be rewritten. We can say that f of x as x plus 1 over x plus 2 and use the quotient rule on that. Or we could say that it's x plus 1 times x plus 2 to the negative 1. And perhaps we can't express that as a product and use the product rule there, but we have to talk about this thing here. How do we take the derivative of something like this? So we'll see that with the chain rule. And 3.7, I believe. So the chain rule deals with how do we take the derivative of a composition of functions. But once we have those rules, then we could look at this either way, take the derivative and get the exact same result. The other thing now with this rule is if we had to find the derivative of 1 over, let's say 1 over x squared, we could use the quotient rule on this. Or we could say that algebraically, I know 1 over x squared is equivalent to x to the negative 2, and I could just use the power rule here. So then once we start expanding our derivative formula, there's multiple ways to look at certain kinds of functions. So the power rule here with 1 over x squared, we say that it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So then this is x squared times the derivative of 1, which is 0. 1 times the derivative of, or sorry, minus 1 times the derivative of x squared. And then we have all of that over x to the 4th. So you have negative 2x over x to the 4th, which can be simplified. And so we simplify that. Simplify this as negative 2 over x cubed. It is easier to write it as x to the negative 2 and just apply the power rule to that. When we apply the power rule here, you have negative 2 times x subtracting 1 from the original power, negative 2x to the negative 3. Rewriting that with positive exponents, that's negative 2 over x cubed. So both work. It's just, recognizing that as a power, it's just a little bit more efficient. If you failed to do so, there's no harm in that. It's just a slightly lengthier problem. That's it. So in fact, when we look at the derivative of sine and cosine, remember the other trig functions, the other 4 trig functions can be written in terms of sines and cosines, like tangent sine over cosine. Once we know the derivative of sine and cosine, we can take the derivative of tangent by writing tangent as sine over cosine and using the quotient rule. Same thing with the other trig functions. So having multiple derivative rules does make taking derivatives simpler, but in terms of the limit as h goes to 0, all of that. But in another sense, it sort of adds a little bit more complexity in another way. It's kind of like the law of compensation. You got air in a balloon and you squeeze it. The air's got to go somewhere. So it's one or the other. So this function, x squared e to the x over x squared plus 1. When we look at a function like this, what you're seeing is you're seeing a product up top and a quotient, right? So the overall structure of that function, though, is it's a quotient. So we have numerator, denominator, it's a quotient. We have to apply the quotient rule to that. Even though we see a product up top, we're not looking at that yet because we're not taking the derivative of just the top by itself. We're taking the derivative of the function, which is a quotient. All right, everybody agree? So when we take the derivative initially, we have to use the quotient rule to take the derivative. Any other derivatives that show up in our formula, we can take them off to the side and look at those. What are they? Are they products? Are they another quotient? Is it a power rule? What is it? So we're just going to apply the quotient rule initially. Okay, so we take the bottom times the derivative of the top minus the top times the derivative of the bottom. And then we divide by the bottom squared. Okay, so that's what we're left with. Once we fill in this derivative and then the other derivative, then we have the derivative. We just have to compute these derivatives individually now. Is everybody okay with where we're at? So we just said the quotient rule. That's what it gave us. X squared e to the x and x squared plus 1. So over here, off to the side, somewhere else, I'm going to take the derivative of x squared e to the x, and I'm going to take the derivative of x squared plus 1. Because those are the two derivatives that showed up. What's the derivative of x squared plus 1? 2x. Now, when we look at the derivative of x squared e to the x, we have to apply a quotient rule. So now we're going to apply the quotient rule to this. It's the first times the derivative of the second. And so if you could imagine if this were like x squared times e to the 5x, you would have other derivatives to compute. So this is really where it's super important to look at these derivatives sort of on a formula by formula basis, one step at a time. So that's the first times the derivative of the second plus the second times the derivative of the first. Sorry, it's e to the x times the derivative of x squared. Is everyone all right with that? Now, this kind of secondary derivative also has other derivatives that we have to compute. So in keeping with how we're handling this, off to the side, we're going to compute the derivative of e to the x and the derivative of x squared. So the derivative of x squared is 2x. Derivative of e to the x is e to the x. So those are, those are like tertiary derivatives, right? Secondary derivatives here that showed up in our quotient rule. So these two derivatives, we're just going to put in place of these two derivatives. So that's x squared e to the x plus e to the x times 2x. So we'll write that at 2x e to the x. 2x e to the x. So depending on the function, you could end up taking the derivative of a single function, or you have to take the derivative, 4, 5, 6 different times, depending on what that function is composed of.
Do you just replace them?
So don't lose track of where we're at. These two derivatives were part of this product rule. Now, this product rule that we've computed here was part of our quotient rule above. So then we're just going to put this in place. Does everybody have what they need before we go back up, or do you need a minute? Okay, so we have x squared plus 1 times the derivative of x squared e to the x, which was x squared e to the x plus 2x e to the x. So that's that. Minus our x squared e to the x times the derivative of x squared plus 1. And all of that's over x squared plus 1 squared. Any questions on what we've done so far? So as far as the derivative is concerned, that's it. That's our derivative. Algebraically, perhaps we could simplify this.
Do Do it.
But that's the derivative. Right? We have no more derivatives showing up after we've said out loud or in our head the derivative formula. There's no other derivatives showing up. So that's our derivative. That's unsimplified, but that's our derivative. On the exam, I wouldn't have you simplify something like that. There's probably a couple of ways to arrange those terms and simplify. So not only is it easier for you not to simplify something like that, but it's also easier for me to grade your problems when hopefully when everybody's work is just consistent. Then when we start simplifying, there's various things we can do. Space, I'm going to do that. I hope that page doesn't come out too small when you print that. If you are, print it down. One of the major components in simplifying stuff like this, especially when you have mixed functions, exponentials, logarithms, trig, whatever, the main idea is to look for the greatest common factor. So that's what we want to do here. This first term in the numerator, let's expand that out, meaning distributing the x squared plus 1 to both things in purple. So we distribute the x squared plus 1. That way we can look at these individual terms. The last term in the numerator, x squared e to the x times 2x, we'll write that as 2x cubed times e to the x. And then up top, all we do is look for what's the greatest common factor, and we're going to factor out the greatest common factor.
You could take out x e to the x.
Yeah, so we can take out an x from all three terms. We can take out an e to the x, and we can take out an x. So we'll just make a note, greatest common factor, x e to the x. Yeah, that's not acceptable. Is that okay? I'm kind of scared to mess with it. So we're factoring the x e to the x out of all of these terms in the numerator. So that leaves us with the x squared plus 1 times x plus the x squared plus 1 times 2 minus 2x squared. Now don't think anything's going to cancel with the denominator, but we'll leave it as a square. And that's the main idea of simplifying something like that. Now we notice what we have in our bracket is just a polynomial. We expand all of that, combine any like terms, and maybe try to factor. But that's the main idea when you see these kind of ugly looking functions that you have to simplify. You want to think about the greatest common factor. Because if we think about now, I want to know perhaps when the derivative is 0, well, this whole thing is 0 when the top is 0. So when x times e to the x is 0, or when what we have in brackets is 0. So let's see what this comes out to be. We've got x cubed plus x plus 2x squared plus 2 minus 2x squared. So x e to the x. In the brackets we have what? No x squared. We have an x cubed plus x plus 2. All over this.
Oh.
All right, so that's simplified version of our derivative. Simplified. I'm also curious if x cubed plus x plus 2 will factor.
I think I messed up way up here.
So I'll come back to that in a second. X plus 1. All right. I mean, that'll factor, but it's kind of a moot point because maybe the only reason we would factor is if we could get an additional factor of like x squared plus 1 up here, we could cancel one of those x squared plus 1 factors. But since that's not the case, I'll just leave this like this. So my point earlier on in the semester was, you know, like this much of that problem is calculus, taking the derivative, right, and all the derivative rules. To get from the derivative down here, the rest of it's algebra. So at least half of this problem involved just algebraic techniques. And that's why you'll find a lot of things that we look at through this course. You know, there's like this much calculus, and then the rest of it's like solving, simplifying, you know, factoring, whatever. Any questions on this derivative here? That was from homework. We could come back to that. It's very similar to the problem we just did. I want to start this, at least one application. Don't see a whole lot of applications of derivatives until 3.6, which is primarily like position, velocity, and acceleration, and then in 3.11 with related rates. So we don't see a whole ton. Population of cells given by the following function, where t greater than or equal to 0 is in hours, and the population is measured in millions. First thing we want to compute is the instantaneous population growth rate and identify the units. So what are we asked to find here?
Acceleration.
No, we have instantaneous. Does that sound familiar? Yeah, slope of the tangent line, derivative. Instantaneous growth rate. Remember the instantaneous rate of change? That rate of change part is a placeholder depending on the context you're in, right? So here we're measuring population, so instantaneous population growth, that's our rate of change. Instantaneous. So we're asked to find p prime of t. P prime of t, the derivative function, gives us at any time how quickly was that population growing. At one moment in time, how fast was that population growing? Okay, so it's a quotient. So we take the quotient rule, where we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So we have t plus 3 times the derivative of 400t. What's the derivative of 400t? 400. Minus 400t. The derivative of t plus 3
1.
is 1. All over the bottom squared. So what happens here? Distribute the 400, you 400t minus 400t plus 3 times 400. So the top just simplifies to 1200 all over t plus 3 squared.
How would you know when to expand the bottom? When would you want it to cancel?
So when you would expand the denominator in the quotient rule, if there was a factor of t plus 3 up top that you could cancel. So remember, since these are separated by subtraction, you can't just cancel that t plus 3 right there. It's this thing divided by t plus 3 squared minus 400t over t plus 3 squared. But if there's potential to get a factor or two,
Meaning the result.
yeah. The result, just always leave it unless you can cancel it.
What if you don't know?
If you don't know, feel free to expand it. There's nothing wrong with expanding it.
If we have both answers and we expand it wrong, would you take the one with the squared?
No. I would say no, so people don't do that. Because I don't want people to do that. I don't want you to have 3 different answers and leave me to guess which one you want me to choose as the correct answer. So that's our growth, instantaneous growth rate, p prime of t. So now this function tells us that if I'm given any time, I can measure how quickly this population of cells was growing. And I don't think we've quite talked about the units of the derivative yet, but now we need to talk about them. When we take a derivative, what are the units?
Something over something else.
Yeah, right? The derivative was defined as, first of all, we took the difference quotient, the change in y over the change in x, and then we let that change get very, very small, right? But nonetheless, the derivative just measures a tiny change in y. Tiny change in the y values over a tiny change in the t values, or the x values. So the units of your derivative, the units of derivatives will always be the y units divided by the x units, anytime you take a derivative. whatever the y, I don't know, maybe we should put parentheses over the x. Because it's not always x and y, like this is not x and y, so I don't want that to be confusing. If it is, then it's always the dependent units divided by the independent units.
So this would be like millions per hour.
Yeah. So the units of y, the function, population was given in millions, and t was given in hours. So the units for our derivative, p prime of t, has units. Million or millions per hour. So if I say the derivative is 3, then I know that, well, let's talk about that because we need to kind of piece it together. But is everybody all right with that? Units, y over x, and dependent over independent. So for example, if we compute p prime of 0, what do we get? Well, that's 1200 over 9 divided by 3. So if we say p prime of 0 is 400 over 3, what we really mean is 400 million over 3. Sorry, 3 hours rather. And does anyone have a calculator? What's 400 divided by 3?
133.3336.
133
The repeating 33.
with a repeating 3 million millions per hour. So what is our interpretation of p prime of t equals 133.33 million per hour? So first of all, it's positive, which means what?
It's increasing.
Oh, it's increasing. We're gaining cells, right? If it were negative, that means the population's dying off at that instant. So initially at t equals to 0, the growth rate of the population was 133.3 million cells per hour. That's a pretty rapid growth rate, right? Like if you start off with whatever number and it's gaining 133.3 million cells per hour, it's the rate of change there is pretty rapid. So that's what the derivative is measuring for us. We will finish that on Wednesday.
Why did you use 0?
Just we could use, once we have p prime, we can use any t value.
Oh, okay, so it's arbitrary.
Yeah, so like if I wanted to know, like, you know, after 2 hours, how quickly was the population growing, I would just plug 2 in there.
Okay.
So yeah, we should probably specify that.